In this video, we're looking at excess and limiting reagent reactions, some of the trickier reactions we look at in preliminary and HSC chemistry. And before we do, we're going to go to revising chemical equations. So when writing a chemical equation, we calculate what's called the molar ratio of reactants and products. So for example, the reaction between magnesium and nitric acid, we have this ratio here, 1 magnesium to 2 nitric acids to produce 1 magnesium nitrate and 1 hydrogen gas molecule. And what that means as far as the moles are concerned, 1 mole of magnesium atoms react with 2 moles of nitric acid molecules to produce 1 mole of magnesium nitrate and 1 mole of hydrogen gas molecules. And this ratio, this mole ratio between the reactants is sometimes called the stoichiometric ratio, the exact ratio of reactants, so they're both completely consumed and turned into products. However, in practice, we often don't get a stoichiometric ratio, particularly in chemical laboratories. Often you add one chemical in excess so the other one completely reacts. So for example, in this case, it's usually you dissolving the magnesium in acid in the lab. You'll actually have excess acid in the test tube. We call this the excess reagent, so that we know that all the magnesium is going to react. But if the acid's in excess, the other chemical, in this case the magnesium, is called the limiting reagent. And it's called the limiting reagent because once it's consumed, the reaction stops. So for example, in this case, once the magnesium is all used up, the products are limited by how much magnesium there actually was, because once the magnesium is gone, no more magnesium nitrate and no more hydrogen gas can be produced. Let's look at this visually. So here's our reaction again, magnesium plus 2 nitric acids goes to magnesium nitrate plus hydrogen gas. And we're going to look in a minute at this question, what happens if you react 2 moles of magnesium with 8 moles of nitric acid? But let's just recap what's actually happening in this question, look back at some redox as well. So here's a little key. These circles represent hydrogen, the yellow circles represent nitrate, grey circles represent magnesium, and grey circles with 2 little holes in it represents the magnesium ions, i.e. the fact that it's lost 2 electrons. Let's have a look. We start off with a magnesium atom, and according to the equation, if we have 1 magnesium atom, we need to react it with 2 nitric acid molecules, so HNO3 are the nitric acid molecules. And what happens is it turns into magnesium nitrate, 1 unit of magnesium nitrate, and 1 hydrogen gas molecule. And you can see there it's all balanced, 2 nitrates, 1 magnesium, 1 magnesium, and 2 hydrogens and 2 hydrogens. What's actually happening in that reaction? Let's think back to redox. Well, we've got this magnesium atom, which we know is a reactive metal, and metals want to give away electrons, and what that magnesium can do, it can give its electrons to the hydrogen atoms from the nitric acid. And so the hydrogens take away those electrons, forming a covalently bonded hydrogen molecule, and now we've got 2 negative nitrate ions and a positively charged magnesium ion, so they bond to form magnesium nitrate. So that's what happens in this reaction. So let's look at the question now. This time we haven't got this nitrate ratio of 1 to 2, we've actually got 2 magnesiums and 8 nitric acid molecules. So let's see what happens. Well, first of all, one of the magnesiums will donate electrons to 2 of the hydrogens from 2 of the nitric acids, so now we've got 1 magnesium ion and 1 hydrogen molecule and these 2 nitrate ions. The rest are still nitric acid. The second magnesium, it'll donate 2 electrons to 2 of the hydrogens here, forming another hydrogen gas molecule. Now we've got 2 magnesium ions and 4 nitrate molecules and 4 unreacted nitric acid molecules. The magnesium and the nitrates, well, they're going to bond together to form magnesium nitrate, and that's what we're left with. We're going to be left with 2 magnesium nitrates, 2 hydrogen gas molecules, and 4 unreacted nitric acid molecules, and no magnesium. So let's look at the maths of that. To look at the maths of this, we've got to think about, well, how many are left over? We've got to ask ourselves, how many moles do we start with? How many moles actually reacted? And that will tell us how many remain. So in this case, we had 2 moles of magnesium, 2 moles reacted, we had none left over. For the nitric acid molecules, we had 8 to start with. Now we had 2 times 2 reacted. Why do we have 2 times 2 reacted? Because we had 2 moles of magnesium and the ratio is 1 to 2. So that means 2 times 2 or 4 moles of nitric acid had to react. So 8, take away that 4, means we've got 4 left over. How many do we produce? Well, we started off with no magnesium nitrate, but we produced 2. Why do we produce 2? Look at this mole equation. 1 magnesium for every 1 magnesium nitrate. So both our magnesiums were consumed, turning into 2 magnesium nitrates, and the same for hydrogen. We started off with 2, with none, we added 2, now we've got 2 molecules of hydrogen gas, because once again the ratio between magnesium and hydrogen is 1 to 1, and therefore if we consume 2 magnesium atoms, we're going to produce 2 hydrogen molecules. So what does that mean? Well, that means the magnesium must be the limiting reagent because it was all consumed. The nitric acid must have been in excess because some remained at the end, and the amount of products was limited by the moles of the limiting reagent. So the amount of products we had here was limited by how much magnesium we had, because that was the limiting reagent. And this logic of thinking about what's limiting, what's excess, how many we start with, how many reacted, how many produced, and how many remains is the way you solve limiting excess questions. So as an example, we've got example 21 from our notes. And example 21 says nitrogen and hydrogen react to form ammonia. If 15 litres of nitrogen react with 4 litres of hydrogen, it should have said at 25 degrees and 100 kilopascals. Please add that in. So if that reaction takes place, first of all, present a chemical equation for the reaction. Now, you should know that nitrogen and hydrogen are both elemental gases, they're diatomic gases. You should know the formula for ammonia, so pause the video and see if you can figure out the chemical equation for this reaction. Hopefully you figured out that one nitrogen molecule reacts with 3 hydrogen molecules to produce 2 ammonia molecules. Next year in Year 12 we're going to make this an equilibrium sign rather than an arrow. We'll find out why that is a bit later on, but for now this is fine. The next part of the question, calculate the moles of nitrogen and hydrogen. So what data have we got? Well, we've got to find the number of moles, we've got to figure out the molar volume and the volume of each one. Using the data given, well, we know that number of moles is volume divided by molar volume. The molar volume here is going to be 24.79 based on the data we've provided, and we know the volumes of hydrogen and nitrogen are 40 and 15 litres respectively. So number of moles equals volume divided by molar volume for both of them. That gives us these numbers here, but if we look at the question here, we've got 2 significant figures for the nitrogen and 1 significant figure for the hydrogen. That means both of them to be different significant figures. So the hydrogen should be just 2 moles, 1 significant figure, and the nitrogen should be 0.61, which is for 2 significant figures. Third part of the question, which species is in excess and which species is limiting reagent? This is the critical step to solving these problems, figuring out which one's in excess and which one's limiting. So I'm going to say from the ratio, from our equation here, from this ratio, we can say the moles of nitrogen divided by 1 should be equal to the moles of hydrogen divided by 3. That's what should happen if it's a nice stoichiometric ratio. Or we can rewrite that as the moles of nitrogen should just be 1/3 the moles of hydrogen. So we know we've got this 1.613 moles of hydrogen. Note I've gone back to the full value because when you're doing your calculations you use the full number, not the rounded off number. For this 1.613 moles of hydrogen, how many moles of nitrogen do we need? Well, we're going to need that number divided by 3, which is 0.538 moles. So to completely react our 1.613 moles of hydrogen, we only need 0.538 moles of nitrogen. But if you look over here, we've actually got more nitrogen than that. And what that means is we've got more nitrogen than required, so therefore nitrogen is in excess, and that means that hydrogen must be the limiting reagent. It means the hydrogen is going to run out before we've completely run out of nitrogen. So this is how you figure out the excess and limiting. The chemical that runs out first, in this case hydrogen, is limiting. The one we've got too much of is the excess, the nitrogen. So now we come into the last 2 questions. It's calculate the number of moles of ammonia produced and the moles of nitrogen and hydrogen that remain at the end of the reaction. And for these sort of questions, limiting excess, when you're finding all the things about the products and reactants, sometimes a table is the best way to go to solve these problems. And the table looks something like this. First of all, what species have you got? How many moles of each did you start with? How many you actually reacted? How many were produced? And therefore, what's the final moles? So what species do we have? Well, we have hydrogen, nitrogen, and ammonia are the 3 species in question. We've already calculated in the previous question, in part 2, that we have 1.613 moles of hydrogen and 0.6051 moles of nitrogen. I've just gone back to the full values for our calculations here. We also start off with no ammonia. There was no ammonia at the start because it's one of our products, it's not one of our reactants. Next thing is how much reacted. Well, whenever you have a limiting excess reaction, the limiting reagent is always consumed. So limiting reagent is completely used up. So in this case, the hydrogen, 1.613 moles must have been used up. The nitrogen, we've already calculated this. How much nitrogen reacts? Well, to react this 1.613 moles of hydrogen, we only need 1/3 as much nitrogen, which in this case is that 0.538. That's how many moles of nitrogen actually reacted. And how many moles of ammonia reacted? Well, none. It's not one of the reactants. It's one of the products. How much is produced? Well, obviously we don't produce any hydrogen and nitrogen because they're our reactants, but we do produce some ammonia. And the amount of ammonia we produce is limited by the amount of hydrogen we had. So to calculate the moles of ammonia, we've got to figure out based on the ratio to hydrogen. We always figure out things based on their ratio to the limiting reagent. And looking at our equation, it's going to be number of moles of hydrogen divided by 3 equals number of moles of ammonia divided by 2. Or the number of moles of ammonia is just 2/3 the moles of hydrogen. So putting our moles of hydrogen in gives us 2/3 of 1.613, gives us that 1.08 moles of ammonia is produced. Last step, the final moles. It's always how much you start with, take away how much reacted, adding on how much is produced. So for hydrogen, we started off with 1.613, we used up 1.613, therefore there's no moles left. It's not a limiting reagent, it all gets used up. Our excess reagent, nitrogen, that was not all used up, we started off with 0.6051 moles, we reacted 0.538, we got 0.067 moles remaining. And last but not least, we got our ammonia. We started off with none, but we did produce 1.08, so we got 1.08 moles. Now to go to significant figures. So because hydrogen was our limiting reagent, we used the moles of hydrogen in all our calculations in figuring how much nitrogen reacted, and how much ammonia was produced, and therefore we use this value, the 40 litres, as our foundation of all our calculations. Therefore all our numbers have to go into one significant figure. So it's 0 moles, 0.07 moles, and 1 mole.